这个天空是给这个24年1月这个东西，那后面其实出了好多的动力的元素，对，你这个
那举个例子，实际上10年8年早晚你从事，这么去它咱们，我们是一个道理是干这个事情，一定需要后面的话，实在没有办法在边缘，就在边缘20点0点6边缘。
现在我们有12点6点说，不是开一个你里面改得到这个能挺重好的能力，已经提不大了，是不能力的这个产品。
Can you have close the door? Yeah. Okay. Let's start. My name is Wenhai. I'm from Hawaii. I'm from China. Yeah. Today I will talk something about the challenge and the opportunity for AI in the Telco cloud. And that is we are facing some sustainability requirements. So here is a background. The sustainability development has reached consensus in ICT field. So based on the Paris Agreement of United Nations, we need to reach the carbon neutrality by 2050. So there's some organizations like ITU, GSMA, SBTI, they have collaborate and achieve a major roadmap for the carbon reduction with global operators. So that's three main target for the carbon emission for fixed network, for mobile network, for data center. Drop at an average of 50%. Now we are in the 6G generation. So the 6G organizations such as ATS, Exchange, NGMF, they have agreed that this green and low carbon is the key features of the future. So this is the energy efficiency methodology. That is defined by ETS and 3GPP. The energy efficiency of our mobile network is decided by two key characters. One is the data volume run on 5GC or the next generation, and the energy consumption. So by dividing these two parameters, you get the energy efficiency for the mobile network. So here's the chart or example I shared. The real need and the actual power consumption and the real optical power consumption, there's a big gap. So that's what we can see. So this gap is the technology can give you. So the main theory here is that you need to consume power on demand. Okay, so you can reduce your workload or improve the management. By reducing the workload, you can reduce the ineffective load like using caches or do some comparisons to improve the performance. And for the management, that is the way you manage the gap. So one is that you allocate your resource accurately with no fragment, or you can dynamically manage the power you use for a specific hardware. So when in low traffic or business, then you can manage that. You can add a power off, sleep, or change some in nature. So here is based on the theory before, we have a proposal of the solution is the Telco Cloud Green Brain. It has 3 layers. For the it has the brain for control for the output region to get the load aware and also dynamically to change the power and also the atomic features provided by the hardware level for you to control. So for the controller, you will manage the policy of the energy saving, or you can work closely with the applications. You can sense the traffic, all the things from the application layer. You have the metrics, and with the metrics reported by the hardware, you get that which is idle, which is in low mode, which is busy. So you can change the frequency. You can reload or rescheduling with this, or you can you can evaluate the power used by that specific node or that hardware. Then you can change its mode. Yeah. And with the hardware, I will talk more later about what's the feature that provided by the CPU. It's better for you can sleep or offload, or you can power off and on, or measure the traffic. So I'll take one server as a typical example of server. You can see that there is the power used by node, and if you calculate that 6% of that is used by the CPU, so that's the major part. And if you go through the method of each component, what can we do and what we achieve that besides CPU, you also have some method, but some of them you can. It's not the effect is very minimal, or some of them you can save some of it, but the total usage of that device is very small. So the benefit is small. So our strategy is that we focus on CPU, and with CPU we have our theory to save it. That is, we can measure two key parts. One is the frequency of the CPU. One is that its state. So the total usage is based on dynamic usage is that the frequency, and static one is that either it's power off or it's using. So we do a test based on our environment that we have a very light load on the CPU, and they are in lowest frequency, and then that's the limit for CPU that you can save 30 to 35% of the CPU if it's in very low mode. That's what we can say. You need to run, but it's still active. Yeah. If you here's one solution for the CPU is that if it's actually not in use, then you can sleep it. So most CPU provide a state for you to manage that. You have working state or sleeping state. Yeah. So the benefit for if you set to the C6 state, then it may save you 2.5 to 4 watts for one single CPU. And the theory here is that in our Telco cloud deployment, most of the workload is pre-installed, pre-allocated, and we see that there's an average of 20% of the CPU is not allocated. So at that part, we can sleep them for temporary, and if there's more workload coming, then we can reuse them. And what's more that if you release a washing machine, and based on the brain we have and the policy we have, then it can sleep the new released CPU into this mode and to save power. Yeah. And we know that besides the core, the CPU has the other components, the M-core ones, and actually they can also save your power. If actually the policy here is that if the and the core is running at a base frequency, then we will not change anything. But if it's done that, we will adjust the frequency dynamically based on the core itself. So this part can save you 20% of the power of a single CPU. So with the metrics reported by the CPU, you have the brain want to control the business level power savage, then you have a place to observe them. So we first to calculate and sorted this hardware based on our rules and sizes, and then we will collect two data. One is that the historical data for prediction, and for the latest data we'll get them for the real time adjustment for the hardware state. Here is one example that for scenario that you have deploy your workload at the beginning, and you see that there is an idle server in your platform, then you can power off them. And to make sure that you will not affect your business, then you need to periodically keep them alive. Power them on, and check everything is fine, then power it off. Yeah. So also we also have some reliability features to make sure that there is no accident power off to make sure all server in a good state. And we see that as I mentioned, in the Telco cloud is all workload is pre-allocated, so there is a fragmented fragmentation in each node. And one way is that you sleep all the core, and another way is that you resolve this defragmentation. You can migrate them into several servers or tens of servers you want to run, and then you have some idle servers. And use the previous ways that you can power off the idle server and use the previous feature to save this. Yeah. There's one feature that in Telco Cloud we use DBDK for the package transmission. So there's one symptom is that DBDK will use 100% of the CPU, no matter it's running a real traffic or not. So it does not know the real business requirement, but it's running 100%. So in this part, we need the high level to know that you have real package. So if not, then we will collect back your CPU usage and down your power. So in this part, it can save you. For example, if you only have 10 to maybe 30% of your CPU load, then it can save you 1.2 watts per core. Yeah. Okay. So in Telco Cloud, actually, I think it's not only our characteristic. In other business, I think they also have this format. You have your peak hour, you have non-peak hour. So ours is like this. You call in the day and you sleep in the night. So if you have this one, okay, you can predict and you can scale as you wish to reduce your core base of your server, and then predict this try and power of them, and you can reduce 4% of that in 24 hours. So okay, that's all the way we have right now for the energy saving. And so when we are introducing AI technology right now, actually this is in development phase. So we are seeing that requirement for the dashboard of the intelligent energy consumption. So to achieve that, actually we are seeing that the requirement for the hardwares for the intelligent like GPU or NPU, the lack of the API or the interface for you to collect the signal or to control them. We see only CPU have this right now. So we're hoping that GPU, of course, the current industry is trying to use 100% of GPU right now. But now we also see requirement that if there's really idle GPU or we can cut its power supply, so you can save the power. Yeah. So with the prediction part, we're introducing AI to predict that one, make sure it's more accurate to say more. Yeah. And with that, we are trying to reuse the maintenance agent, not a new one, so that it will not introduce more consumption by the prediction itself.
Yeah.
Yeah. So yeah. That and the energy saving strategy recommendation by AI and used for applied by the people. Yeah. So yes, and this is a thought not mature, but now we see that it is not the hardware, not the scheduler, but the whole system you need to consider to save your power. So from the high beginning, like for example the modern AI, you need to specification, quantification, to make your prediction, to this computing to make sure that your model is efficiency. And for the platform layer, you need to have the scheduling, the operators, and also for the accelerators, you need to memory close computing, you need to replace FP64 by 8, or you need to have a access localized storage. So you need to combine this algorithm, scheduling, and also the combining the accelerator design, the whole part, make sure that your application running on the most efficiency hardwares, and you also have a system to manage the power saving strategy. So that's our thought for this system level from high level to low level, this optimization is a good choice. Yeah. Yeah, that's all for me. So no questions. Thank you. Yes.
So I saw in one of your slides, one of the options you provided was offload to GPU. For power savings or power optimization. Do you have any data points there? Because DPU will also consume power, right?
Yeah, that's a good point. Yeah. That depends on the work you are offloading. Based on my observation that we offload a lot of work from CPU or GPU, that's package dealing work. And that's for DPU, they are designed for that. So actually, its performance may be over 10 times to CPU. So it will save power by this.
For what kind of work?
Package encoding, decoding.
Oh, package
encoding,
decoding.
Yeah.
You think that performance
for the
DPU
general computing will not offload to DPU.
Understood.
Yes.
Okay.
Yeah. Yes.
So you framed this quite a bit in terms of sustainability.
Yes.
And you showed graphs of like the consumption of energy, the actual consumption of
Yes.
the use of your capacity during the day. I was wondering, do you have any data yourselves on like the footprint of the available energy during the day? Because I can imagine that during the middle of the day, there's obviously much more solar panel power available than at night. So, like, I'm saying that the impact might be even bigger than you are just seeing by raw power, because, like, if you use less power at night.
Okay. Okay, I see. That's a good question. I think that issue may be to industry like the public networks or things, but Telco cloud actually is the private closed ones. It's for the workload like your phone calls, and actually its access is limited to the public end users or things. So the power consumption is only affected or most affected by the calling traffic.
Yeah.
So the impact is, so the prediction actually we see is very precise.
No, that I understand.
Yeah.
I'm just saying, like, so you could quite quickly make a translation into watts, right?
Mm-hmm.
But if you go to like CO2 emissions,
What mission?
CO2 emissions,
Okay, yeah.
like the CO2 emissions per watt of energy used at night is probably higher than it would be during the day, because at night you're going to have to use more fossil fuel because there's no solar energy. That's
Okay. I
so
see.
I was wondering, do you have any data on like how much CO2 do you use per watt during the day, and how much CO2 do you use during the night?
Okay, I guess your question. Actually, that's beyond my knowledge.
Okay.
We only see the watts
Right.
because we only study the technical part. Yeah. Yeah, that's for the business for consideration.
Yeah. Okay. All right.
Yeah. Yes.
To add something, sustainability is not also only about energy, power consumption and so on. It's also about the life cycle analysis, the manufacturing impact and so on.
Mm-hmm.
So do you plan to perhaps take that into account when you choose new servers? Perhaps try to choose, let's say, ARM because they tend to be more energy efficient, something like that. So do you plan to integrate more metrics in the end?
I think so, but as you know, we are first. I want to answer that we do use the machines, and that's our major servers. Okay, that's one thing. And secondly is that our product line responsible for this cloud. And that's one is built for our common IT department, and I see that they are drafting some document and this supply chain things. They do have it. Yeah.
Okay.
Yeah.
Okay.
Questions? Yeah.
Perhaps another one.
Yes.
It's more specialized. So you spoke a little bit about C-level, and C-level tends to be different between manufacturers. So AMD tends to have less support of lower C states, so they tend to save less energy.
Mm-hmm.
So did you test different architectures? Because I think that the C6 is only available on Intel.
Yeah, I take that as an example. Yeah. Actually, we use Intel and our own design ARM the CPUs.
Okay.
For AMD, actually, it's not. I think we do not include that in our solution anymore, so we have no so, yeah, information on that.
Okay. Thank you.
Yes, more? Okay, that's all. Thank you.